We'll now talk about high-energy diffuse backgrounds, which are in X-rays or gamma rays, and their origins, which are mostly from active galactic nuclei. This picture is an X-ray image of the Moon from the Rosat satellite, and you can see that the illuminated side of the Moon is reflecting X-rays from the Sun. The Sun does emit some. And there is a dark side of the Moon with some X-ray events even from there. There could be in the foreground of anywhere between Earth's atmosphere and the Moon. But there is also a notable excess background behind the dark side of the Moon, which shows clearly that their origin is beyond Earth-Moon system. And those are the X-ray photons of the diffuse X-ray background. The cosmic X-ray background was actually discovered before the cosmic microwave background with the very first astronomical X-ray experiment, which was rocket-borne test led by Riccardo Giacconi, who many years later got Nobel Prize for this. And they detected first sources such as Scorpius X1, but also diffuse X-ray emission that seemed to be coming from everywhere. And at that time, it simply wasn't known where does it come from. For comparison, it is about 1% of the diffuse optical or far-infrared background that we talked about it when we talked about galaxy evolution, which essentially is integrated starlight ever emitted from galaxies. And that itself is in percent level relative to the cosmic microwave background. So in terms of sheer energy density, these backgrounds are relatively negligible, but their astrophysical interest is very considerable. We now believe, and actually very certain of this, that most of the X-ray background originates from active galactic nuclei. It's been resolved in individual sources. Some of it comes from star formation in galaxies, say supernova remnants and such, but most of it comes from active nuclei. There was, however, one major puzzle, and that was the X-ray spectrum of the background. So here is a very wide bandwidth plot of various cosmic backgrounds, from radio through almost gamma rays. And you can see that microwave background, the black body curve on the left, dominates the picture. This is log-log plot. And so then there is optical or near-infrared or far-infrared background, and then there is X-ray background, schematically illustrated with that wiggly line. The black dot in the lower right is the cosmic gamma ray background. So what about the spectrum of the cosmic X-ray background? Here is a plot of measurements from a variety of different satellites that have been doing that. Sometimes overlapping in energy, sometimes not. You can see that there is a little bit of spread between them, and that's just issues of cross-calibration. It's not so easy to calibrate these things. Now, this shape of an X-ray spectrum is typical of the very hot gas, so thermal Bremsstrahlung radiation. You have a hot plasma, electrons are passing by protons, all ionized. They're decelerated by electric interaction, they emit photons. And so it's not like a Planck black body, but it's thermal emission nevertheless. And that would imply on the face value of it that the universe is somehow filled with hot plasma, and this is where it comes from. But that doesn't work because we simply haven't seen it. Instead of that, we see a lot of active galactic nuclei in X-rays that are identified optical radio sources. But the problem is that their spectra don't look like this. So how can you have collective emission with a spectrum that looks like thermal emission from plasma composed of a lot of non-thermal sources? It turns out to be a combination of their evolution in time and redshift and slightly different ways in which X-rays are being released. Some of it comes directly from synchrotron electrons. Some of it comes from reflected actinium emission from dust surrounding the active nucleus. The way to find this out was to obtain really deep images in X-rays of selected patches in the sky and then try to identify the sources. This was done in Hubble Deep Field and other deep fields that are done. Chandra telescope had its own deep fields, one which overlapped Hubble, the other one in the south, and so on. Typical exposures for these were in millions of seconds, so a lot of invested time in these observations. And as you can see, there are plenty of X-ray sources. They look sharp in the middle, and they look big on the outskirts, and that's purely the effect of the X-ray optics. It's not so easy to make X-ray mirrors, and so the image quality deteriorates in radius. They're not really bigger, they're just images are fatter on the detector itself. And this is precise enough that we can actually seek optical or radio counterparts. We can also count the sources and see if the total emission from all of the sources counted to the faintest level adds up to the overall integrated background. And the answer is it pretty much does. And so in different energy bands, you get counts to a different depth, but they follow more or less the same kind of curve, which is some sensible evolutionary models. And if you extrapolate to fainter source counts, because they're reasonably well behaved, just like in the optical, there are reasonably well behaved counts of both active nuclei and galaxies, you can account for easily for 90% of the total observed X-ray background. And the remaining 10% could be just uncertainties of extrapolation. So what are the X-ray sources? Here is a collection of a whole bunch of Chandra sources identified in the optical, and a lot of them look point-like. These are active galactic nuclei. Sometimes you can see the galaxy, those are relatively nearby ones. But by and large, they all seem to be associated with non-thermal activity in quasar-like objects. Interestingly enough, some of these do not show any signs of a non-thermal AGN in the middle in optical. So the visible or UV or infrared light is completely hidden, but X-rays do penetrate the dust and we see them. It turns out that there is not a good correlation between X-ray and optical fluxes. Something can be a very luminous X-ray source and very faint in the optical, or vice versa. And they come in different nature. If we plot here X-ray flux versus essentially optical flux, you see there is no correlation whatsoever. And sources of different kinds appear in different way. There are some galaxies which are powered by star formation, and those tend to be lower luminosity X-ray sources, whereas active nuclei, like quasars, tend to be higher luminosity X-ray sources. Redshifts were measured for a whole lot of them. They turn out not to be particularly high redshift objects, most of them out to redshift 2 or so, typical for quasars. And here are essentially what's Hubble diagrams of sorts for the X-ray sources. Although it's not apparent flux, it's absolute luminosity. The reason you don't see faint sources at high redshift is that they're just too faint to detect. But you can see they do extend to very high luminosities, and essentially all of the ones at high redshifts, which are solid squares, are active galactic nuclei. What about gamma rays? Story there is very similar. Beamed active galactic nuclei, those with jets, are not to be the principal extragalactic gamma ray sources, aside from gamma ray bursts, which are spectacular but do not contribute much energy overall. This is a sky map from Fermi satellite after first year of operation, and you can plot it in galactic coordinates and see Milky Way plane has a lot of gamma ray emission from a variety of sources. But outside the plane, there are point sources, and essentially all of them are associated with active galactic nuclei, and specifically with blazars. After a few years of work with Fermi, they actually could add up light from non-blazars, and turned out that they do not add up to the full observed gamma ray background. So those are the obvious sources, but there could be extra kinds of sources that might be contributing. Well, some of the catalogs of these beam AGN are probably incomplete on a factor of 2, probably, because when measurements were done, source was in low state, so never made it into a catalog. But even so, there isn't enough in the known active galactic nucleus population. Additional sources could include some star formation where gamma rays come from shocks and supernova remnants, or even shocks in gas. And it was also proposed that some component of dark matter may be decaying and emitting gamma rays, although so far no evidence was seen for that whatsoever. So there could be also fainter populations of beam active nuclei that somehow didn't catch our attention earlier, perhaps because they're too faint. So this is still an area of ongoing work, but still beam active nuclei are probably the main contributors. Something else interesting is that beam nuclei, blazars, can produce photons on tera-electron volt energies. Typical gamma ray observations would be at giga-electron volt energies or mega-electron volt energies. But these things go out to tera-electron volts. They can be actually observed from the ground. Earth's atmosphere is opaque to the photons themselves, but these high-energy photons can knock out particles from atoms or molecules in the upper atmosphere and give them some kinetic energy. And then you have charged particle moving at a very high speed, which can then emit so-called Cherenkov radiation, and those can be seen with large telescopes on the ground. So here are the light curves of several of the blazars in tera-electron volts, and they've been also detected in the optical. It turns out their Lorentz factors are excess of 50, and that was interesting in itself. This gives us some confidence that probably the highest energy cosmic rays also come from these beam active nuclei. Remember, those are accelerators in the sky. And interestingly enough, the highest energy cosmic rays are 100 million times more energetic than particles in Large Hadron Collider in Geneva. So there are many uses for these cosmic accelerators. First of all, they probe the demographic signification of active nuclei. They're an obvious contributor to the cosmic gamma ray background. There is a lot of physics of relativistic jets that can be learned from them. And there may be the ultimate sources of high-energy particles. So there could be the future of particle physics, because we'll never have an accelerator that is 100 million times more powerful than Large Hadron Collider. They do other interesting things. For example, they're very compact radio sources, and they're the only important radio source foreground population to the measurements of cosmic microwave background at high angular resolution. So they have to be accounted for precisely before better cosmological conclusions are drawn. And they can also serve as a probe of star formation, even though they themselves have nothing to do with star formation. And the reason for that is that intergalactic starlight came from all the different galaxies, as well as the microwave background, are opaque to high-energy photons. And this sounds a little weird, that a gas of photons is opaque to other photons. But in the center of energy of the two photons, one of which can be from infrared and the other one is really high-energy gamma ray, they're both high energy, and they can exceed pair production energy for positrons and electrons, so the two photons interacting can turn electron-positron pairs, which later annihilate somewhere. But essentially, intergalactic starlight forms a fog for high-energy gamma ray sources. And so if you can measure the cutoff in their energy as a function of redshift, you can probe energy density of intergalactic starlight without recourse to any redshift survey or any deep counts, which is a nice independent way of constraining the history of cosmic star formation. And here is another plot, slightly expressed in a slightly different way, of all the different cosmic diffuse backgrounds. They're diffuse when you don't have a good resolution, but all of them except cosmic microwave background break into individual sources once good enough observations are obtained. And roughly speaking, in radio, it's mostly from active galactic nuclei, but there's some star formation. Microwave background has cosmological origin. Sub-millimeter, far-infrared, visible, and near ultraviolet all come from star formation, obscured or not obscured. X-rays mostly come from active galactic nuclei. Some small component comes from star-forming regions. And gamma rays, as far as we can tell, mostly, maybe entirely, come from active nuclei, even though we haven't accounted for all of them yet. And next, we will turn to the study of the evolution of active galactic nuclei.